Hi everyone, Professor Rosenthal here, and today we're going to take a look at the section on integration with use substitution, but specifically with the use of exponential and logarithmic functions. So this is lesson 3.3b in our Blackboard course. And let's first remember something from the past. We've learned way back how to differentiate and exponential and logarithmic functions. So for example, the derivative of e to the x, you may recall, is the easiest function there is to differentiate, right? And it is e to the x itself. And what about the derivative of ln x? I hope you also remember that, how to differentiate the natural log function. And the derivative of ln x is, does anybody remember? If you said 1 over x, you are correct, 1 over x. So these are the two rules we need to remember. Now that you know the derivatives, the integrals are going to be pretty straightforward. So the integral of e to the x, think about it. Which function, when differentiated, gives you e to the x? And if you said e to the x, you're absolutely correct. But of course plus c to make it more general, because any addition of any constant will still make it an antiderivative for that, because when you differentiate e to the x plus 5, for example, it still gives you e to the x, right? Now what about the integral of 1 over x? Well, since we know the derivative of ln x is 1 over x, the integral of 1 over x will be natural log of x. But natural log is only defined for positive values, so we're going to put natural log of the absolute value of x plus c. And again, you can check it, because derivative of ln x for positive values will truly give you 1 over x, and so that is a quick way to see this will work. Now you might say, wait a minute. You know, the integral of 1 over x, couldn't I do it this way? Couldn't I do it like this, right? As x to the negative 1 dx, and apply the power rule, right? So add 1 to the power, you get 0. Divide by the new power. Oh, we're dividing by 0, which is not even defined, right? So at that point, I want you to realize, because it's easy to forget this rule, okay? It's a lot more likely students will begin by applying the power rule when they see 1 over x. But at that point, I want you to remember, when you realize you have to divide by 0, and that is undefined, I want you to remember there was another rule for this. This is a special case. This is a case where the power rule of anti-differentiation does not work. It works every other power, right? Negative power, fractional power, positive power. But when it's negative 1 power, it doesn't work, and we must use a special rule with the natural log function. Alright, so now let's do a few examples. By the way, in practice, instead of e to the x dx, you might also see e to the u du. It's really the same exact thing, and it will still be e to the u plus c. So whatever this variable is, that variable will show up in the final answer. And if you're integrating 1 over u du instead of 1 over x dx, same idea, right? It's going to be natural log of the absolute value of u plus c. Just whatever this variable is, that's what's going to be reflected in your answer. Let's do a simple one, e to the 2x dx. So if u is equal to 2x, then du equals 2 dx. So first I'm doing a quick u substitution here, because it doesn't look exactly like the rule that we had, right? If it was just e to the x, the rule works, or just e to the u, the rule works. But e to the 2x, we have to do a quick u sub. So now this becomes e to the u, and instead of dx, what can I write? Look over here, dx is the same as du over 2. So take the 1/2 outside. Now we have e to the u du, and that we know how to do. Just e to the u plus c, and put the u back in there. We get e to the 2x plus c. So I want you to remember something as a result of this example here. Let's put it as a rule, okay? This is going to come up a lot. It's good to know this. If you have e to the constant times x dx, the answer is going to be 1 over that constant times e to the kx plus another constant. You remember when we differentiate e to the 2x, it was e to the 2x times 2. So when we anti-differentiate e to the 2x, it turns out to be e to the 2x divided by 2. And for something like that in the future, I would say you don't even do the u sub. Just we're going to write the answer as, like if I give you, what is the integral of e to the 3x, for example? Integral of e to the 3x dx. You could just say it's going to be 1/3 times e to the 3x plus c. And you don't even have to do u sub, okay? Okay, but something like this we do need to use sub. So integral from 0 to 1 of 3x times e to the x squared plus 1. So the first thing you have to figure out is what is a good u selection for a u here. So let u be equal to what? And the same principle from the last class applies. Let u be a quantity so that its derivative is already embedded in the integrand up to a constant. So if we let u be x squared plus 1, this will appear like e to the u in the next step. It's getting easier looking, right? So, but we're going to need to know what is x dx. So for that, differentiate both sides. Du equals 2x dx. So x dx is what we're going to need eventually, is du over 2. So we come over here, factor the 3 outside. Okay, so this is what is going to become e to the u. And the x dx is the part you have to figure out what can I replace that in terms of the u variable. So x dx is the same as du over 2. And over 2 part I'm going to put it on the outside. So a complicated looking integral has been made so much easier after the u substitution. And that's the whole goal, right? We want to go with this complicated integral in terms of x to a much simpler integral in terms of u. And now we have 3 over 2 times the antiderivative of e to the u du is e to the u plus c, and keep the 3 halves up front, but the only thing you have to do is bring the u back, and u being x squared plus 1, we have our final answer, 3 over 2 times e to the x squared plus 1 and plus c on the outside. Now for this question, I forgot that we also have the limits from 0 to 1. So if there were no limits, that's how you would leave it. But because there are limits, what I'm going to do is now I'm going to erase the plus c and go ahead and plug in the limits from 0 to 1. So keep the 3 halves on the outside of everything, can be factored out. Plug in a 1 for x. 1 square is 1, 1 plus 1 is 2, so we have e to the second power minus, plug in a 0 for x, and you're going to have e to the 0 plus 1 or e to the 1. So we can leave it like that, or we can even factor out an e, because I see e squared minus e. So take out an e, and we can also leave it as, in parentheses, e minus 1. So you can convert to a decimal, but you can also leave it in the exact form. Usually I prefer the exact form anyway, so it's good to be familiar with that format. Okay, a few more examples, but this time involving the natural log function. I'll come back to this in a minute. Let's do an example with the natural log function. So we have examples such as integral of 7x over x squared plus 1. What would be a good selection for u here? If you said x squared plus 1, you are definitely on the right track. Temporarily, as our intermediate step here, we differentiate, right? From u to du, we have to differentiate. We get 2x dx. But going back to this integral, we need to write everything in terms of the u variable. So for that, the bottom is what we call u. The 7 can be taken outside. And the x dx, let's solve for x dx here. X dx is the same as du over 2. So put the du on the inside, over 2 on the outside, or you can factor it out in the next step, but I like to take the constants out as soon as possible. Okay, at this point we have the perfect form, 1 over u du. And that we have just learned is going to be natural log of u in absolute values plus c. And that is also the same as natural log 7 over 2 times ln of in absolute value. Since u is x squared plus 1, bring that back in. And honestly, x squared is always positive, plus 1 is always positive. In that particular situation, it's okay to drop the absolute value sign if you choose to. So we can also leave it like this. Okay. All right. Any questions? So I know I'm going over it relatively quickly because I know you have the pause option. You can make it go as slow or as fast as you'd like to do on the video. And I always recommend, sorry to be repeating this over and over, but pausing the video from time to time and trying the problem before you even look at the solution. I think that's really helpful. That's the best way to learn as you're watching the video. If you just watch it like a movie, it's just not going to be very helpful. Do it as if you were in the classroom. Typically in the classroom, I stop, I give you some time to work on it, and then we continue together. So it's really important for you to do the same thing when you're watching it at home. All right, let's do another problem involving the exponential function. I think I'm going to get a new page for that. Okay, here we go. So how do we do this one again? It looks quite complicated at first. What would be a good choice for you here? If you said let u be x to the 8, you're absolutely correct because its derivative, 8x to the 7 dx, is already in the integrand up to a constant. Like if we get rid of the 8, there's already an x to the 7 dx up there, right? And in preparation for that, I'm going to need x to the 7 dx in a moment. Let's solve for that. We get du over 8. So going back to this integral, this is the part that's going to become e to the u, right? Because x to the 8 is u. So that's going to be e to the u. The 4 will be factored outside. And what to do with everything else, which is x to the 7 dx. Luckily, we've already done the work for that. X to the 7 dx is du over 8. And the 1 over 8 part can be taken outside next. So it's going to become 4 over 8 times the integral of e to the u du. Now, do you know how to integrate e to the u du? And this can be simplified as simply as 1/2 on the outside. Remember, that is the easiest integral, right? It's itself. Just like it was the easiest function to differentiate, it's the easiest function to integrate. So this one does not have limits, so I'm just going to put plus c. All I have to do is put the u back in place. So it's going to become e to the x to the 8 plus c. And again, there's an easy way to check this answer. Differentiate all of it and see if you get the original question. So derivative of e to the u is e to the u times u prime. U prime is, you differentiate the power, you get 8x to the 7. 8 over 2 gives you 4. Notice you already had a 4 there. And you have an x to the 7. There was an x to the 7 there. And you have e to the x to the 8. So you have the same exact original question. And so that's your proof that this is indeed the correct antiderivative. Okay, one more example involving the natural log function. This would be a great example for you to take a moment let's see, where is my example? I may have to copy and paste it. Alright, so here's your next example. Please take a few moments to try to do this on your own, and we'll come back and continue on in just a moment. Alright, hope you had a moment to try to do this problem on your own before looking at the solution. So now let's take a look at it together. So let u be equal to x to the 9 plus 15. So du equals 9x to the 8 dx. Looking up there, I know I'm going to need x to the 8 dx, so I'm going to solve for that, which is du over 9. At this point, this whole integral, I can take the 6 outside, the denominator becomes just a u, the x to the 8 dx will be replaced by du over 9, so it will become the following. So take the 6 outside, the denominator is u, the x to the 8 dx, x to the 8 dx is the same as du over 9. I put the du on the inside over 9 part on the outside. And I'm putting dot 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 at the moment, meaning that these are placeholders at the moment. I'm not going to worry about the limits. I'm going to bring them in after I have the x variable. Okay, so you can simplify this now as 2/3. Divide each side by 3, you get 2/3. And this is the integral of 1 over u du is the same as natural log of u in absolute values. The u is in absolute values. Again, we have placeholder for the limits. Notice there's no more integral notation because that has done its job. We have done the entire differentiation. Now I have a line. I'm going to evaluate this in just a little bit, but don't be tempted to plug in the limits right now because those limits are not set for u. They're set for x. So don't plug them in just yet. First, bring the u variable back, which is x to the 9 plus 15. So you have 2/3 times x to the 9 plus 15 from 0 to 1. At this point, plug in the upper limit, and you can factor out the 2/3. So you have 2/3, then in parentheses, natural log of 1 to the 9 is 1 plus 15. So that's natural log of 16 minus, now plug in 0, you get natural log of 15. At this point, you can leave it like that. That would be fine. Or you can remember the rule, ln A minus ln B is ln A over B. You can write it like that. Or you can get a decimal using your calculator. So that would be another way to possibly leave the answer. Alright, so in this lesson we looked at some examples of u substitution, specifically the type of problems that involve natural log of x and e to the x. And I'd like to end this section with a warning, and then later I'm going to try to do another session on mixed problems. But the warning is, once you cover this section, it's very tempting to try to do every problem with natural log. Even when you see something like this, let's say you end up with du over u squared. Can you do this one with natural log? I'm going to put a big question mark here. Can you do this natural log of u squared? And the answer is no, big no. Cannot do it that way. You see, natural log only works when you have 1 over u du. Okay, in every other case, if you ever end up with 1 over u squared du, what should you do? Do not use natural log. So instead you should be using the power rule. For something like that, you would say, okay, this is u to the power of -2, add 1 to the power, divide by the new power, etc., right? Or if you have, let's say, the square root of u du, something, let's say du over square root of u. Again, please do not try to use natural log here. Don't say this is natural log of square root of u. It doesn't work. Natural log function only works when you have 1 over u du. For something like this, you have to write it up as u to the -1/2 du, and you need to solve it that way. So I'm warning you, a common danger is, after this lesson, to use natural log for every problem. It cannot work that way. It does not work that way. So be careful. On the homework for this section, I threw in mixed problems. Some that will require natural log, others that will require the power rule. So you need to look at the question carefully, decide which one applies better, and then apply that technique accordingly. And the last example I'd like to take a quick look with you is this one right here, the integral of 5 times sine x times e to the cosine x. What would be a good choice for you here? Let u be sine x or let u be cosine x? If you said cosine x, you are correct. The derivative of cosine is negative sine x dx. Because if you let u be sine, its derivative is cosine x dx, but there is no cosine x dx here. There is e to the cosine x dx, but there is no cosine x dx. That's why this version of the substitution works, the one that we have up there. Now going to the integral, take the 5 out. This becomes e to the u and sine x dx. Divide both sides by -1, so it'll be du over -1. So du can go on the inside, over -1 can go on the outside. So 5 over -1 is just -5. Integral of e to the u du is e to the u. And don't forget the plus c. And as always, bring the u back in terms of the x variable. So u is the same as cosine. Sorry, I should have said u is just cosine x. Its derivative has a dx, but u is cosine x plus c. How can I check this? Differentiate it. Derivative of e to the cosine x is e to the u times u prime, right? So it'll be e to the cosine x times negative sine x. And negative sine x times -5 would give you the 5 sine x. So that's a very quick way to check it using the chain rule. All right, again, lots of practice is how you can really feel proficient about this section. So I would highly encourage you maybe to read the problems from this lesson and then attempt as many homework questions as you can. And also, don't forget, you also have the group activity problems with the solutions in Blackboard website. For this section, it's so important to do lots of questions. Remember, this section is foundational for Calc 2 and for the rest of this course. So very important to build a solid foundation. See you next time.